Hello again guys and welcome back. So in the previous video we looked into the equilibrium between a sparingly soluble ionic compound with its ions in the solution. In this video we will look into another type of ionic equilibria, that is a compound with lone pair of electrons can react with a metal ion. In this video, these are the learning outcomes. At the end of this lecture, you should be able to define complex formation reactions, identify the types of ligands, discuss the formation of coordination compounds and its stability, compare and contrast monodentate ligands and chelates for suitable complex symmetric titrants, and discuss the coordination number and structure of metal ligand complexes. Complex formation reaction occurs when a metal ion reacts with an electron pair donors, which are termed ligands, in solution. Now, let us try to consider this chemical reaction as shown in this slide. The metal ion cobalt accepts the donated electrons is called the central ion or the central atom. In this sense, the metal ions are Lewis acids or electron pair acceptors. The ammonia, or NH3, contains a lone pair of electrons and donates it to the central atom. Ammonia is called the ligand and it is considered as a Lewis base. A Lewis base is a compound that can donate a lone pair of electrons. The product of the resulting reaction between cobalt ion and ammonia is referred to as a coordination compound, a metal ligand complex, or simply a complex ion. Now, I've used a pair of dots to emphasize the pair of electrons that is donated to cobalt. In subsequent reactions, we will omit this notation. Overall, this reaction can be described in terms of chemical equilibria, which I will discuss in the succeeding slides. Now let us look at these ligands. Remember that ligands must contain a lone pair of electrons that can be donated to the central ion. These electron pair donors are called Lewis bases. Ligands can be classified as neutral ligands, meaning they do not have a net charge. Examples are water, ammonia, and amines. Ligands can also have a net negative charge. Examples are shown in this slide. All ligands shown in this slide can donate only one pair of electrons. Such ligands are called monodentate ligands or unidentate ligands. Among these ligands, an interesting ligand is the thiocyanate or the SCN negative. This ligand can attach at either the sulfur or the nitrogen atom of the central atom. These ligands are known as ambidentate ligands. Let us look more closely to the structure of complex ions or metal ligand complexes. A complex ion is an ion comprising one or more ligands attached to the central metal cation with a dative bond. Now, a dative bond is a covalent bond between two atoms where one of the atoms provide both electrons that form the bond. The ligand uses their lone pair of electrons to form a dative bond with transition metal. Metal ligand complexes or complex ion can be described in terms of what we call as coordination number, which is simply the number of metal ligand bonds. In this example, cobalt is our central atom. Chlorine and ammonia are our ligands. Since there are 5 ammonia molecules and 1 chlorine atom in the coordination sphere, therefore the coordination number of cobalt is equal to 6. Now let's look at the molecular view of what is happening during a complex formation reaction. So we have a theory that explains this, and this is called the valence bond theory. So this theory views the metal ligand bond as a polar covalent bond in which the electron density is closer to the ligand than to the metal or the central atom. This theory predicts that the metal ligand bonds will be formed by using the ligands with a shared pair of electrons. The metal ions accept a pair of electrons from ligands via unfilled orbitals. Each ion forms complex ions with the most stable structure possible for a given ligand. Now, I will explain this in the following slides. Let us consider the copper-ammonia complex. The copper cation is a D-block transition metal. It is a small cation with high charge and have available 3d and empty 4s and 4p orbitals of low energy. The empty 4s and the 4p orbitals in the copper 2+ ions are used to pick up pairs of non-bonding electrons from the 4 ammonia molecules to form the tetraamine copper 2+ ion. As I have previously mentioned, coordination numbers defines the number of metal to ligand bonds. Strictly speaking, the coordination number includes the number of metal water bond as well as the number of bonds with other ligands. The coordination number can tell us the shape of the complex ion and how the ligands are arranged around the central atom. A coordination number of 2 exhibits a linear structure in which the ligands are on opposite sides. The following complex ions are expected to have a linear structure. The coordination number 4 exhibits a tetrahedral structure or occasionally a square planar structure. Usually, divalent ions of group 1b, 2b, and 4 exhibit a coordination number 4. A coordination number of 6 exhibits an octahedral structure. Imagine 4 ligands that are on the same plane of the metal ion and the other 2 ligands are above and below the plane. So we have already seen how a complex formation occurs and the structure of complex ions or metal ligand complexes. Let us now talk about the complex ion equilibria. Usually, metal ions exist in aqueous solutions as hydrated species. So this means that metal ions are usually surrounded by water molecules. For example, if you dissolve silver nitrate in water, silver ions are readily surrounded by water ligands as shown here. Dehydrated silver ions usually contains 2 water ligands, although most of the time water is not included because its complex ion is always present in aqueous solution. If the ligand, let's say ammonia, is added to a solution that forms a stronger bond than the current ligand, which is water, then ammonia is going to replace the current ligand, which is water, to form your diamino silver complex. In general, chemical equilibrium is reached where the forward reaction rate is equal to the reverse reaction rate and can be described using an equilibrium constant K. Complex ion equilibria have their own unique equilibrium constants known as the formation constant or Kf. Now, the Kf or the formation constants describes the formation of a complex ion from its metal ion and ligand as shown in this reaction. This constant can also be called stability constant, or in some textbooks they call this as the association constant. Now, as for any other equilibrium, the larger the value of the equilibrium constant, in this case this is Kf, the more stable the product or the complex ion. You can also check your reference books for a table of the formation constants between a metal ion and different classes of ligands. Consider for a metal ion reacting with a ligand to form the metal ligand complex, the equilibrium constant is denoted by Kf or the formation constant. When a metal ligand complex dissociates into its corresponding ions in the solution, this can be described by a dissociation constant or Kd, which is simply the reciprocal of Kf. Many complexation reactions occur in stepwise fashion or in different steps. For example, the replacement of water molecules from the hexa-aqua copper 2 complex by ammonia occurs in 4 successive steps as shown in this slide. We can omit the water molecules bound to copper 2 ions for simplicity. In each step, ammonia replaces one water molecule and has a corresponding equilibrium constant denoted as K1. The equilibrium constants K1, K2, K3, and K4 are known as stepwise formation constants. These formation constants describes the successive addition of one ligand to the metal ligand complex from the previous step. The sum of the stepwise reactions is the overall equation for the formation of the complex ion. Take note that in this example, the hydrated copper 2 ions contain 6 H2O ligands, but the complex ion that is produced contains only 4 ammonia ligands and not 6. The overall equilibrium constant for the steps 1 to 4 can be determined by multiplying the stepwise formation constants K1, K2, K3, and K4. Now in this case, the equilibrium constant Kf is correctly identified as the cumulative formation constant, which is symbolized by beta 4. 4 because there are 4 steps. Take note that the cumulative formation constant beta is equal to the product of the stepwise equilibrium constants K1, K2, K3, and K4. Now, for this specific example, the cumulative formation constant has a value of 2.1 times 10 raised to 13. Now, let's discuss the effect of adding a ligand in a solution containing a slightly soluble precipitate. Now, what happens to the solubility of a sparingly soluble salt, let's say silver chloride, if a ligand that forms a stable complex ion is added to the solution? To find the equilibrium constant for the complexation reaction that includes a solid, we combine the appropriate KSP and the KF expressions. In general, the solubility of an ionic compound containing a metal cation that forms a complex ion increases in the presence of aqueous ligands. Let us look at the silver chloride in equilibrium to its silver ions and chloride ions. The KSP value for this reaction is known as 1.82 times 10 raised to negative 10. Consider, for example, if we add ammonia, which is the ligand to this solution, the ammonia will react with the silver ions to form silver ammonia complex, and this has a KF, or a formation value, of 1.7 times 10 raised to 7. Now, the magnitude of the equilibrium constant, which is 1.7 times 10 raised to 7, indicates that almost all of the silver ions in the solution will be immediately complexed by ammonia to form the diamino silver complex. Now, adding the two reactions together will give the new equilibrium constant, which is just equal to the product of the KSP and the KF. Okay, so what does this tell us? Overall, the addition of the ligand to a solution containing silver chloride in equilibrium with silver and chloride increases the solubility of the silver ion. Alright, so let's try to solve a common problem in complex formation reactions. In this problem, we are asked to determine the concentration of copper ions at equilibrium after mixing two solutions. So the problem is a 200 ml of 1.5 times 10 raised to negative 3 molar of copper nitrate is mixed with 250 ml of 0.2 molar of ammonia. What is the copper ion concentration at equilibrium? Okay, so the first thing that we have to do here is to write the reaction between copper ions and ammonia. So we have here the reaction of copper ions reacting with 4 moles of ammonia to give you a diamino copper 2 plus complex. So we have to write this in terms of its formation constant, and this is simply the molar concentration of the complex ion divided by the molar concentration of the copper ions multiplied to the molar concentration of ammonia raised to the power of 4. And looking at the KF values in your reference book, this has a KF value of 1.7 times 10 raised to 13. Now remember that you have two solutions here that you've mixed, so therefore the copper and ammonia concentrations are different. So we have to find out the new concentrations of copper ions and ammonia ions in the diluted solution. In this case, we can use the dilution formulas, that is C1V1 is equal to C2V2. Take note that the total volume is just the sum of the volumes of copper nitrate and ammonia. So that is 200 ml plus 250 milliliters. Of course, you have to convert this one to the proper units of liters. So the final concentration for copper is 6.7 times 10 raised to negative 4 molar, and the final concentration for ammonia is 1.1 times 10 raised to negative 1 molar. Now we can create an ice table and plug in the values for copper and ammonia. Notice that the formation constant has a very large value, so assume that almost all of the copper ions is converted into the complex ion. So at change, we write negative 6.7 times 10 raised to negative 4 for the concentration of the copper ions, negative 4 multiplied to 6.7 times 10 raised to negative 4 for the concentration of ammonia, and positive 6.74 times 10 raised to negative 4 for the concentration of the complex ion. At equilibrium, there is a tiny concentration of copper ions left, and we designate this as X. Now, take note that even though we have a large value of Kf, we must expect that there is still a very small concentration of copper ion that is not complex by ammonia or free copper ions. For ammonia, at equilibrium, the concentration is 0.11 because this is the excess reactant, and the complex ion will have an equilibrium concentration of 6.7 times 10 raised to negative 4. Alright, so the next thing that we have to do is to substitute this equilibrium concentration values to our Kf expression as shown in this slide. Again, X here corresponds to the concentration of free or uncomplex copper ions. Solving for X, this will give us a value of 2.6 times 10 raised to negative 13, which is an extremely low concentration. Of course, we are expecting a very low value for this because of the large value of Kf, which means that most but not all of the copper ions have been converted to the complex ion. Alright, so in the last 3 slides of this lecture, we'll look at more closely at ligands. Previously, we have discussed unidentate inorganic ligands. We have seen that monodentate refers to the ligand that donates only a pair of electrons to the central metal atom. In contrast, molecular ligands can donate 2 or more pair of electrons to the central metal ion. For example, bidentate ligands have 2 donor atoms which allow them to bind to the central atom or ion at 2 points. Polydentate ligands range in the number of atoms used to bond the central metal atom, so we shall see some examples in the following slides. Tridentate ligands have 3 donor atoms which allow them to bind to a central metal atom at 3 points. A common example is the diethylene triamine. As shown in this figure, the nitrogen atoms each have a pair of electrons that can be used to bond to the central metal atom or ion. Tetradentate ligands have 4 donor atoms which allow them to bind to the central atom at 4 points. As shown in this figure, the nitrogen atom each have a pair of electrons that can be used to bond to the central metal atom. And lastly, a hexadentate ligand is an example of a polydentate ligand that has 6 donor atoms with electron pairs that can actually be used to bond to the central metal atom. A common example is the ethylene diamine tetraacetic acid, which is often abbreviated as EDTA. This is a hexadentate ligand and can bind the metal ion via 6 sites. That is, 2 from the nitrogen sites and 4 from the oxygen sites as shown in this image. Generally, complex ions with polydentate ligands have much higher formation constants than those with monodentate ligands. This additional stability is known as the chelation effect, or simply the chelate effect. Okay, so this is the last topic in lecture 4 and we are already done with module 1. I will see you in the synchronous discussion.